Yeah, I just have to see if I can see you right now. You're a little too far over.
Hold on. There we go.
Yeah, you're good.
You good?
Yeah.
Okay. Hello everyone, my name is Siddhant, and in the past few months I've been working on researching into advanced methods of rocket propulsion for interstellar travel. So today I'm here with you to share my most recent project, which is using computational fluid dynamics to observe inefficiencies in rocket nozzles. The number you see on the screen right there, the number 30, that's how many years we have until things really start to go downhill for us. I'm talking about events such as soil infertility, flooding, and habitat loss becoming even more and more prominent. We've seen these types of events in the past, and it's inevitable that they will occur in the future, potentially at an even bigger scale. To help preserve humanity, it's important for us to become a multi-planetary species. Multi-planetary species are species that are spread out across more than one planet. The benefit of being a multi-planetary species includes new hubs of innovation, further space exploration, alongside a dispersed population. Mars is close in proximity with Earth, although it has its own challenges that we need to overcome before we can fully start to terraform the red planet. There are also habitable exoplanets out there in the universe. These habitable exoplanets are in the habitable zone or Goldilocks zone of their star. Basically, this area is an area where the sun gives off enough heat and sunlight to foster life for the planet. The only problem with this is that they are so far away that it's virtually impossible for a conventional rocket to take us there in a person's lifetime. For example, it would take around 30,000 years for a chemical rocket to reach Proxima b, which is an exoplanet in our closest solar system, Alpha Centauri. On the other hand, it would only take 40 years for an antimatter rocket to do the same thing. While this is great, there are huge barriers to implementing or even testing out antimatter propulsion systems. The first one being with cost. It's going to take a lot of money to build the rocket and also test it out. The second is with time. It's going to take a lot of time to fully test out the rocket, reiterate, and just to make sure that it is up to its maximum efficiency. Luckily for us, there's a solution to this, and that's with computational fluid dynamics, or CFD. CFD essentially works on allowing the user to input their project and try different parameters or designs to make sure that they are able to observe inefficiencies or make their project as efficient as possible. So, in the space tech industry, CFD is used everywhere to help reduce the time and cost it takes for the testing and construction of the rocket. To mimic the use of CFD in the space tech industry, I decided to perform a CFD analysis on the exhaust plumes of a rocket nozzle. To help me with this project, I used ANSYS Fluid, which is the CFD software being used in the actual industry. The first step is with the geometry. The geometry is essentially the overall surface that would be used to display the flow. So the bottom left of this green surface is the rocket nozzle. The starting edge symbolizes the connection between the imaginary combustion chamber and the overall rocket nozzle. The rest of the space is known as a shock domain. The shock domain is essentially where the exhaust plumes will appear alongside the air around the rocket nozzle. The next step is with meshing. So meshing is a quality of life improvement type step in which having a structured mesh will allow you to gain more accurate results alongside improve the time per iteration. The third step is with the exhaust plumes and the overall setup and solution. So first of all, I input some basic information such as the solver type I'm using alongside the space I'm working with, which is either 2D or 3D. Then I went to the models and simply changed some of the default models to more specific models, such as for the viscosity model, I changed it to K epsilon. K epsilon is a CFD model used for more turbulent flows such as the exhaust plumes of a rocket nozzle. After that, I input my boundary conditions. Boundary conditions are basically the overall parameters that the model will use to develop some flow. So the parameters that I input were first of all the temperature in Kelvin alongside the initial gauge pressures for the pressure inlet and outlet of the rocket nozzle. After this, I initialized the overall calculation and then ran my calculation. The way I made my model was so that half of the exhaust flow would appear as it's more effective for what I'm trying to do. In the results tab, I simply took the half of my flow and mirrored it to create my fully symmetrical exhaust plumes. Before I talk about the inefficiencies observed, I'm going to talk about two preliminaries. The first one being a converging diverging nozzle. So the way the converging diverging nozzle works is that the hot exhaust that is produced by the combustion chamber travels into the converging nozzle. After this, the throat of the nozzle basically takes the hot exhaust that is flowing in multiple directions and directions it while the compression makes the exhaust flow travel at the speed of sound. The diverging nozzle is the area where the flow expands. This is done to basically make it so that the flow is reduced in pressure and heat while increased in velocity to ensure that there's a strong and stable flow. Another aspect related with rocket nozzles is when the exhaust plumes exiting the rocket nozzle, if the pressure is lower than the atmospheric pressure, the rocket nozzle is known to be overexpanded, meaning that the exhaust plumes get smaller and smaller near the end of the flow. Another phenomenon with overexpanded nozzles are shock diamonds. So shock diamonds are essentially the pattern of the flow folding in certain ways, which creates these diamonds as you can see on the screen. When going back to our results, we can see that the velocity of the exhaust plumes actually drop off near the end, as you can see with the contours. This is actually a sign of inefficiency, as we want our rocket nozzle to produce as much thrust as possible. The good part is that there's no flow separation. Flow separation is when the outside air starts to push in against the pressure of the exhaust plumes, and this can cause damage to the nozzle. There are also some faint shock diamonds starting to form. This means that our rocket nozzle is slightly overexpanded. This is a sign of inefficiency, as we want the rocket nozzle to be optimally expanded for as long as possible to gain the maximum amount of efficiency. I hope that throughout this presentation, you got to see the potential and impact of CFD in the space tech industry. My vision for this is to use CFD to promote the faster and more efficient development of advanced methods of rocket propulsion so we can travel more of the universe and get to our new Earth at a faster rate. Thank you.